Just say the name, say cesium, and you say chloride. That's all we need. So cesium chloride. That copper one, we need to figure out, hey, what's the charge going to be? So we figured out it was a 2 plus, right? Because oxide's always a 2 minus from the location on the periodic table. We know that oxide's 2 minus. And look where copper is. Okay, so I'm looking for copper, and it's not in group 1, it's not in group 2, and it's not on diagonal. That means I need Roman numeral or Iconos endings. Okay, so that's going to be copper 2. Copper 2 oxide. And then aluminum phosphide, that's a 3 plus and a 3 minus. Be very careful, this is phosphide. We're not calling it phosphate or phosphite, it's phosphide. Very good. And then we have ammonium, NH4 plus, and oxide. So this is ammonium, that's the name of that polyatomic ion. And then the anion is monatomic, so we just say ide, ends in ide. So ammonium oxide. Very good. And then iron. Now iron, we have to look at the cations. We're like, okay, it's not group 1, it's not group 2, it's not a diagonal. So when you're talking about iron, we're going to need a Roman numeral or an Iconos ending. And do we have iron up here? Oh yeah, here we go. Okay, so this is iron and this is sulfide. So we're going to need a Roman numeral here. So we figure out, well, what's the charge? That's a Fe3 plus, so we're going to have to write iron 3 Roman numeral, so iron 3 sulfide. Okay, do you see why we need to put a Roman numeral with it? Based on its location in the periodic table. So you look where iron is, it's in the middle. That means what? I need Roman numeral or an Iconos ending, right? Okay, so it's iron 3 sulfide. Same thing with lead. Okay, so let's take a look at lead. Where's lead located? Does everybody see it on the periodic table? Does it need a Roman numeral or Iconos endings? Yes. Okay, so then you figure out what the charge is. This is 4 plus. So this has to be lead 4. Okay, it's lead 4 because it's a 4 plus. So it's lead 4. And then chromium, same thing with chromium. I'm going to need to put a Roman numeral or Iconos ending with it. So it's chromium 3 bromide, very good. And then we've got sodium and nitrite. So this is called sodium nitrite. And then magnesium is Mg2 plus because it's in group 2A. And then this polyatomic ion, we need to know the name of that. That's the acetate polyatomic ion. So that's magnesium acetate. That's what it's called. And then tin. Do I need a Roman numeral with a tin? Yes, I do. So it's tin 2 because we figured out what the charge was, tin 2 iodide. And the last one is calcium hydroxide, Ca2 plus, and you know the OH minus, so calcium hydroxide. Okay, whoo, we did it. So what do you think? Questions? We got that down? So you can put together an ionic compound, cation and anion, put them together, write the correct subscripts from the charges, and when you name it, you just name the cation and you name the anion. And that's it. Yay, we did that. Okay, so let's talk about naming other compounds besides the ionic compounds. So we're going to name 4 groups. We're going to name ionic compounds, we're going to name molecular compounds, we're going to name acids, and we're going to name hydrates. Now each one of these has its own set of rules. So what we want to do is we want to keep it straight. Otherwise, if you start mixing those rules, then it's just like, wow, there's so many rules, which one do I use? And then you get them all jumbled. So what you want to do is you want to first step, this is key, first step is to decide what kind of compound do I have. And then once you know the compound, then apply only those rules. So you have to look and see what is an ionic compound. And how did we decide we could tell an ionic compound? What did we say? Metal and a nonmetal, or cation and anion, right? So look to see. If you have that, then you name it, as we have been practicing, as an ionic compound. All right. So let's continue with our ionic compounds. We kind of already know how to name that. Remember how we talked about that? You just name the cation and then you name the anion. So for example, this is calcium iodide. It's kind of how we already practiced that. This is the name of the cation is calcium. The name of the anion ends in ide, calcium iodide. That's it. No prefixes, nothing. You just say the 2 names, calcium iodide. Here, though, Remember, if it has more than one type of charge, like for example iron, we had to figure out what the charge is. So this is iron 3, and then chloride ends in "ide." So it's iron 3 chloride. And you know iron needs a Roman numeral because look where it's located on the periodic table. So, and you have to figure out what that Roman numeral is based on the charges, right? So you would say iron 3 and it always ends in "ide." Okay, so we already know how to do that one, and this is a flow chart. You can keep this handy. So once you figure out that you have an ionic compound, keep this chart handy and use it to help you practice the rules. So keep it straight. If you start mixing the rules up, it's going to be very hard to unmix that. So just use that chart to help you decide. But the key is you have to know which compound we're talking about first. Now, the same thing happens with the polyatomic ion. You name the cation, and then you name the polyatomic. For example, this is potassium. We call that hydroxide. So just put the two names together, potassium hydroxide. Here, again, the name of the cation, we need an iron. We did that one. Let's do the one with the polyatomic ion. Okay, so this is iron 2 this time. We had to figure out it was a charge of 2. And then we name that polyatomic ion, which is sulfite. So you say iron 2 and then sulfite. Just put that together, iron 2 sulfite. And that's how we name an ionic compound. All right, so we've kind of already been doing that. And if you don't like a flow chart, I've got a list up here. It does the same thing. But I want you to find out if you have an ionic compound or not and get the correct chart out. And do it that way until you get so familiar with it you don't need the chart anymore. Here's another chart. If you didn't like the other chart, you didn't like the list, here's another one you can use. And this one also has the molecular compounds on it, which we'll talk about in just a minute. All right, remember cations are always listed first. So if we were to name these, how would we name them? So let's start with the first one. How would you name that one? You would say what? Lithium fluoride. Perfect. And that's sodium bicarbonate. Perfect. Now this needs a Roman numeral. Iron 2 sulfate. Iron 2 sulfate. Perfect. Okay, now this one also needs a Roman numeral. Now you have to copper 2 or copper 1? Copper 1. Perfect. Copper 1 chloride, because chloride's a -1. That has to be a +1, so it's copper 1 chloride. How about this one? Oh, what was that one called? Mercury 1 bromide. Potassium permanganate. Good. Potassium hydroxide. Yay! Potassium does everybody remember that as dichromate? Oh, yeah. Okay, potassium dichromate. This polyatomic ion is called dichromate. So potassium dichromate. And this one is called calcium hydride. Ends in "ide." Calcium hydride. Yay! So that was easy. Good job. Very good. Woo! Okay, that's ionic compounds. Now let's do molecular compounds. Oh, wait. How do I recognize a molecular compound? What's a molecular compound made up of? All nonmetals. Okay, so you got to remember that because you got to apply different rules. So first thing you have to decide is you got to look at this compound and decide which group it's in. Okay, that's the key first step. So a molecular compound, how do you recognize that again? All nonmetals. So let's look at that. All nonmetals. The thing about the molecular compounds is I bet you know how to name these already. You've been running around naming molecular compounds. So let's put a couple up and I bet you could tell me what they are. Okay, I've got CO and CO2. What do you call CO? Carbon monoxide. What do you call CO2? Carbon dioxide. Why'd you say di? There's 2 oxygens. Why'd you say mono? 1 oxygen. That's right. So with molecular compounds, this is important. With molecular compounds, you name it using the prefixes like di, tri, that kind of thing. Did we ever use prefixes with ionic compounds, though? Never, never, never use prefixes with the ionic compounds. Okay, if you follow those rules and those charts, there's nothing in there about prefixes. If you look at the molecular compounds, that's where you use the prefixes. And you know recognize a molecular compound because it's all nonmetals. Okay, so we'll need to use prefixes. Are you guys familiar with those? You probably are familiar with most of those. Let's go down to these. Like mono, di, tri, tetra. Okay, tetra, not quattro, right? And you know penta. Penta, like pentagon, is 5. Hexagon, 6. Octopus. Octopus has 8. Decade is 10. There's a few that you may not know. Hepta, that's 7. And nona. Nona makes 9. Nona, 9. Okay, so these are your prefixes that we use. So we're going to use prefixes. That's why you said carbon dioxide, and that's why you said carbon monoxide. Now, these are molecular compounds. They're neutral. That's another thing. No charge, neutral. And when you name the first element, you also use prefixes as well, except if it's a mono. We don't ever say monocarbon monoxide. We just don't use mono with the first element. But you do use mono with the next element, and then you use these prefixes. Okay, that's easy, right? That's not so bad. So that's it. This is the flow chart. Name it with a prefix, say the element, another prefix, and then end in "ide." So for example, P2O5, that would be P2, so that's what? 2 is di. So diphosphorus, because that's phosphorus. And then you got an O5. So that would penta's what? 5 is penta, right? And then O is oxide, so it's diphosphorus pentoxide. Now, as far as spelling goes, penta is the prefix, but it's next to an O, oxide. So whenever you have penta and an oxide, we drop the A. So it becomes pentoxide. Pentaoxide. It's kind of hard to say anyway. So drop the A, and that's the spelling. Okay. Does that make sense? So you just say the name of the prefix, and then the name of the element. Then you use another prefix, and the second element ends in "ide," just like ionic compounds. All right. Here's your list, so let's just go through. Well, the first one we said was carbon monoxide. Okay, mono is not used if the first element, so that's not monocarbon monoxide, it's carbon monoxide. So if you were to go through and name this, let's name all these. Okay, there's 2 nitrogens, so what's 2? Dinitrogen. Okay, 4, what's 4? Tetra, so oxide. So this is dinitrogen tetroxide. Very good. How about this one? This one is 4. What's 4? Tetraphosphorus decoxide. Perfect. How about this one? Sulfur trichloride. The second one ends in "ide, so this is just sulfur trichloride. It's not monosulfur, right? Sulfur trichloride. How about this one? Oxygen difluoride. Perfect. Boron triiodide. Perfect. Carbon tetrachloride. Perfect. Xenon tetrafluoride. Very good. Now this one is an acid. I've got AQ, and the reason why AQ is it's an acid. So we're going to come back and name this as an acid later. But if it was an ionic compound, then it would be hydrogen bromide. Okay, and then this one, sulfur trioxide. There you go. Is that easy? Gosh, you knew that one all along. That's so easy. Now, which one do we use these di, tri, tetra prefixes? Ionic compounds or molecular compounds? Molecular. All right, that's 2. Only got 2 more to go. Okay, so the next one we're going to do is acids. Oh, man. So let's talk about how we name an acid. So first of all, we have to recognize an acid. How do you recognize an acid? Well, we know how to recognize ionic compounds. We know how to recognize molecular compounds. How are you going to recognize an acid? Well, an H. It has an H in it. And where's the H? In the front. It's a front. So, for example, HCl. There's the H in the front. That's an acid. Okay, H NO3, that's another acid. H2SO4, that's another acid. This one, HC2H3O2, that's another acid. But wait, there's hydrogen in the middle. That's okay. That's just the polyatomic acetate ion. The key is the hydrogen is in the front. So acids donate hydrogen ions. And so the one that gets donated is the one in front, not any of these in the middle. So we put the hydrogen in the front. Okay. So everybody can recognize an acid? Yeah, how do you recognize an acid? Hydrogen front. Another key point. This is an acid. This we name as a polyatomic ion. Why is this one? It's got an H in the front. Why are we not naming this as an acid? Because it's an ion. It has a charge. So if it has a charge, it's an ion, and we use the ion naming methods. If it's an acid, it does have a hydrogen in the front, but a key point is that it's neutral. Okay, so an acid then is neutral and has hydrogen in the front. Okay, acid is neutral and has hydrogen in the front. So can we recognize an acid now? Okay, well, how did I know to put 2 hydrogens with this one and 1 hydrogen with that one? The same. What's the same? We said, doesn't an acid have to be neutral? So if this is a 2 minus charge, what does that tell you how many hydrogens have to be there? 2. That's why it's H2SO4. Okay, here's phosphate. Now, if I want to make this be an acid, how many hydrogens am I going to need? 3. That's why it's H3PO4. And nitrate is going to be a -1, so if I put it, that's why it needs 1. How about carbonate? Carbonate's a 2 minus. How many hydrogens do I need with carbonate to make it be an acid? 2. That's right. It's going to be H2CO3. Okay, so an acid is neutral and has hydrogen in the front. Now let's talk about the acid naming rules. We know how to recognize it. Okay, now there's one more thing we need to recognize before we talk about the rules, and that is it a binary acid or an oxyacid? If I say oxyacid, what is that? What are you thinking about? Oxygen. So an acid with oxygen. Binary. Yeah, it's HCl. Binary is, how many is bi is what? 2. If hydrogen is 1 element, then I just need 1 more element. There's not going to be an oxyacid where I have lots of elements. Okay, so binary acid. So is this a binary acid? Yes. Is this a binary acid? No. What is this? Oxyacid. How about this one? Oxyacid. How about this one? Oxyacid. Okay, how about this one? HI. Binary. How about this one? HBr. Binary. How about this one? H2S. Binary. Okay, good. All right, now, we're going to have to go back to the ic and us endings again. Oh, boy. Yay. Use them with the metals, and we get to use them with the acids. Okay, here we go. If you are a binary, there's only one rule. Okay, very simple, one rule. So if you recognize the compound, there's not that many rules. The key is to separate it into the correct compound. A binary acid, we just add the prefix hydro and then ic ending. So this becomes hydrochloric acid. That's it. Okay? So what's this one then? HBr, hydrobromic acid. HI is hydroiodic acid. That's it. Hydro and ic. So hydro goes with the binary acids. Hydro never, ever, ever goes with oxyacids. Okay? So which one does hydro go with? Binary or oxy? Binary. Okay, remember that? Hydro goes with the binary. Never put hydro with the oxyacids. Never put hydro with the oxyacids. Never, ever, ever. Okay, it goes with the binaries. All right, that was that rule. So now let's talk about what happens if we have an oxyacid. Okay, so let's put the oxyacids in here. Let's, for example, chlorate. Okay, this is the name of the polyatomic ion. So you do need the name of the polyatomic ions in order to name the acids. This is chlorate with a -1 charge. So if I put 1 hydrogen with it, it becomes the acid. Now, if it ends in 8, remember we said 8, 1 more oxygen? If I ate 1 more oxygen, I got sick. Okay, ate 1 more oxygen and I got sick. So 8, the polyatomic ion ends in 8, then the acid ending is going to be ic. And if the polyatomic ends in ite, then the acid ending is going to be us. So I ate 1 more oxygen and got sick. You can remember it that way. Another way to remember it is the 2 I's do not go together. Okay, so ite goes to us. So if this is chlorate, then it becomes chloric acid. Did we put hydro with it? No, because didn't we just call this one hydrochloric acid? You can't call this one hydrochloric acid again. So one of them has the hydro prefix and the other one does not. Okay, so we need to make sure we remember which is which. That's hydrochloric acid, and this one becomes chloric acid. And if that's perchlorate, then this is perchloric acid. 8 goes to ic. Okay. And then ite, chlorite, becomes chlorus. No hydros, just change the ending. Chlorus. Ite goes to us. If this is hypochlorite, then this is hypochlorus. There's not a hydro here. Don't confuse that. That's hypo, not hydro. I know there's so many similarities. You're like, ah. Okay, hypo is just part of the name of the polyatomic ion. That's why it's there. We didn't say anything about hydro. This is hypochlorite, so it's hypochlorus. Okay, whoo! Is that making sense? Okay, so what does 8 go? 8 ending, 8 changes to ic, and ite changes to us. And that's all you do for the oxyacids. Just change that one ending. Okay? All right. Now, one thing about the binary acids is if it's a molecular compound, we'll put a G with it to indicate it's a gas, and we name it as we do hydrogen chloride. That's how we would name that one. But if it's an AQ, then it's dissolved in water and it becomes the acid, so hydrochloric acid. So we do kind of have to watch that, hydrogen chloride or hydrochloric acid, depending on whether it's G or an AQ. Do you guys know what AQ means? Aqueous. So we dissolved the gas in the water, and that's how we got the acid. All right, so let's practice with this. Here we have our acid. So here's your acid flow chart. First, you got to decide, is it a binary acid or is it an oxyacid? If it's a binary, we said hydro and ic. If it's an oxyacid, what did we say? A goes to ic or ite goes to us. For example, we already talked about hydrochloric acid. This is phosphoric acid because that's phosphate. This is sulfite, so it becomes sulfurous acid. Didn't we say ite goes to us? So if it was called sulfite, now it's sulfurous. If this was phosphate, 8 goes to ic, it's phosphoric acid. Okay. Let's name the acids. All right, how do we name this one? H2CO3, 8. It ends in 8, so what's the name? It's going to go to what? 8 goes to ic, so that's going to be, instead of carbonate ion, that becomes carbonic acid. Okay, nitrite. Think what happens to ite. Nitrous. Very good. Now here's nitrate. 8, 8. Nitric. Very good. Phosphate. Phosphoric. Perfect. Sulfite. Sulfurous. Sulfate. Sulfuric. Hypochlorite is the name of the ion, so what's the acid? Hypochlorous. Perfect. Chlorite becomes chlorus. Chlorate becomes chloric. And perchlorate is perchloric. Woo, yay! Okay, so we got that down? Yeah, 8 changes to ick. I changes to us. That's how you name an oxyacid. A binary acid, there's only one thing you can do with it. Hydro and ick. That's it. Whew, got that, right? Okay, so that's 3 groups. We're getting there. We're getting there. Okay, so let's go with the 4th group. Okay, and the 4th group is a hydrate. What do you think of a hydrate? Think of water, yeah? Okay, hydrate we think of as water. Now, an ionic compound comes in that crystalline structure, and inside that crystalline structure there's little spaces for a water molecule to get in there. That's a hydrate. Hydrate, think of water. So this is an ionic compound with water in between in that crystalline structure. Now, it's not enough water to dissolve it. Does it look like a solution? No, it's a hydrate. It's got water molecules tucked in there, and the ratio is here. So how do we name that? Well, this is an ionic compound, so we use ionic compound naming rules. So that's cobalt 2 chloride, just like we normally do. And then what do we do about this hydrate part? Well, we're going to use a prefix, and hydrate's kind of a molecular compound, so we're combining the two. So it's cobalt 2 chloride, and then what's 6? 6 is hexa, and we say hexahydrate. So cobalt 2 chloride, hexahydrate. That dot means loosely attached, because you can heat that up and vaporize the water, and then what do we get? We get an anhydrous, just the cobalt 2 chloride, anhydrous salt. Looks a little different color, doesn't it? And you're just driving off the water, and that's a hydrate. Okay, so let's see if we can name another one. Okay, this is MgSO4.7H2O. So here we go. How do we name this? Magnesium sulfate. 7, what's 7? Heptahydrate. We call that hydrate. Okay, so that would become magnesium sulfate heptahydrate. Let's do another one. Okay, this is CaSO4.2H2O. So how do we name this one? Calcium sulfate dihydrate. Perfect. Okay, we got that? Yay, that was the last one. That was the easiest one. Okay, does that make sense? All right. When we're talking about the more the things we know about chemistry, the better. The more we are able to understand the world around us. So this was, I thought, was an interesting story about this 14-year-old who did a science project up in Idaho back in 1997, and he set a petition. Sent that around for people to sign for a ban on dihydrogen monoxide. And he asked 50 people if they supported the ban of that chemical. 43 said yes, we should ban dihydrogen monoxide. 6 weren't sure. 1 knew what it was. So as we think about this, this is what he said. He said, dihydrogen monoxide is colorless, odorless, tasteless, and kills thousands of people every year. And these deaths are caused by accidental inhalation. Wow, you inhale that, you're dead. Pretty dangerous, huh? And it says prolonged exposure to its solid form can cause tissue damage. And for those who have become dependent on dihydrogen monoxide, withdrawal means certain death. You withdraw from dihydrogen monoxide, certain death. There's just no way around that. It accelerates corrosion and rusting of many metals. It's a component of acid rain. Okay, it's reaching a huge epidemic. Despite this danger, dihydrogen monoxide is still used in nuclear power plants, in the production of styrofoam. It's used in the distribution of pesticides, and you try to wash your fruit off with it, and this chemical still remains. Not only that, but regulation, there's not any really. Companies can dump dihydrogen monoxide into rivers and oceans, and nothing can be done to stop them. Not only that, but the American government has refused to ban the production, distribution, or use of this damaging chemical due to its importance in the economic health of the nation. In fact, the Navy and other organizations are conducting experiments with dihydrogen monoxide and designing multi-billion-dollar devices to control it and utilize it in warfare situations. In fact, many highly sophisticated underground distribution networks exist where they can just pump this stuff around. Wow. It's not too late. Sign the petition now to ban dihydrogen monoxide. What do we think? That's pretty serious stuff. That's a pretty damaging chemical. I don't know. 40, what is it? Out of 50 people, 43 said yes, we should ban it. 6 weren't sure. 1 knew what it was. Dihydrogen monoxide. What is it? H2O. It's water. Did you recognize that? H2O, dihydrogen monoxide. That's water. So what this petition was about was to see if people will ban water. Okay? Yeah. But you know, you have to be so careful about what you read out on the internet because this was all hyped up, right? But it was true. You can take true things and twist it to make it sound like, oh, we have to ban dihydrogen monoxide. Okay, well, it's colorless, odorless, tasteless, and then if you inhale it, you die. Yeah, that's called drowning. Okay, and, you know, a solid form, it can cause tissue damage. Yeah, have you ever heard of frostbite? Yeah. If you're dependent on dihydrogen monoxide, which we all are, withdrawal means certain death. Yeah. If you don't drink water and you stop drinking water, that would be bad. We're going to die, right? And if you wash your pesticides with it, it still contaminates your fruit. Well, that's because it was water. Yeah, you still have water on there. And sophisticated underground piping systems, well, that's how you get water out of the tap. When you turn it on, as the water's coming under the ground. So do you see how we have to be very careful about how things are portrayed? And the more you know about science, the more you can read through that stuff because that is just all hyped up. And actually there's fun websites out there talking about banning dihydrogen monoxide. There was actually a town council in California that was seriously going to ban it. And they were getting ready to pass this legislation and somebody came up and told them, oh, guys, it's water. And so they had kind of quietly dropped that. So, yeah. So you need to know about science. The more you need to know, the more it helps you get around stuff like that. Okay, this is the periodic table that we're going to get on the test in the testing center. This is the periodic table that we're going to get. So if you want to know what that looks like, and this is the back side. So if you want to know, oh, what's on the back? What am I going to get? This is what we're going to get. So these are all your flow charts. So what I want you to do is when you practice naming these compounds, I want you to go through and use these flow charts to keep straight the names. And so what I want us to do now is we have a few more minutes. I'm going to put some compounds up on the board, and we're going to number them off, and I want you to write the name of that compound. I'm just going to mix them all up, so you have to look to see which compound it is. The hydrate's not on there because that was the easiest, and then we'll do that. Okay, so we're going to number off, and we're going to start over here, 1, and so I'm going to write these up on the board, and as soon as you see the name of your compound, start working on that, and then you can write the name of that compound up on the board, okay? And then when we're all done, maybe if you haven't written them all done by then, maybe you take a picture of that. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so I'm going to write those up on the board, and you start working on the names. And the first thing you have to do is to decide what group am I in. Okay, which compound does this belong to? Which group? And then you can just write the name by them. Okay, and you can practice naming all of these. Okay, and if you think you have your number right, you can come right underneath it up on the board. Okay, this is actually sodium. Na is sodium. Sodium sulfate. Perfect. Hepta. Okay, no prefixes with ionic compounds. You're right. So you just write nitrite. Perfect. Perfect. Okay, hydrogen. Hydrogen, yeah. This is mom. Did you have 5? You had 5. Okay, that's an acid. That's an acid. Because H is in the front, yeah? So 8 goes to... 8 goes to... Ick. Okay, so that would become chloric. So I've got to recognize the compounds that we're in. Okay, so that would be chloric. Dinitrogen pentoxide, yeah. oxide.
17 is it correct?
17, is it correct? Okay, arsenic. Okay, arsenic is actually a nonmetal. So this is not an ionic compound. This is a molecular compound. It would be good if it was ionic. You would name it perfectly right. But since it's molecular, we use prefixes. So this would be tetraarsenic hexaoxide. Yeah?
Tetra.
Arsenic. Uh-huh. Yes. Yes, it is an acid. So you have to go by the. So go look over there in the acids and decide which acid it is and name it that way.
Tetraarsenic. What oxide?
Hexaoxide. Tetraarsenic hexaoxide. Okay, so it's an acid. Okay, it's an acid, right? It's an oxyacid or a binary acid? Oxyacid. So now you have to take off the H and look at that polyatomic ion. What's the name of that polyatomic ion? Hypoiodite? Hypoiodite. Okay, so ite ends in us, so this becomes hypoiodous acid. Okay? Does that make sense?
But I thought it was...
It's an acid, right? It's not a binary acid, is it? No. So you're only left with ite goes to us and ate goes to ick. So that's how you would name it. You would just change the ending.
What's the name?
What's the name of this polyatomic ion? Ends in ite. Hypoiodite. Okay, so the name of the polyatomic ion is hypoiodite. That's the name of the polyatomic ion. So ite goes to us. Okay, so change the ending to us. And that's it.
What confused me is like, I thought there's no...
That's not hydro. That's not hydro. That's hypo.
Oh, okay.
That's part of the polyatomic ion name, hypo, not hydro. Yeah?
So it's just one of those you gotta remember? Like,
Yes.
Okay.
Yes. No. Hydro. What kind of acid is this? Let's go over there. What kind of acid is it? Is it an oxyacid or a binary acid? It's an acid, so which one? Binary or oxy? Oxy. So what are you doing for oxy? You say, you just, ate goes to ick or ite goes to us. That's all you do. So you know the name of that polyatomic ion, right? What's the name of this polyatomic ion? No. What's the name of the polyatomic ion?
Chlorine.
What's the name of that polyatomic ion? You have to know the names of the polyatomic ion. What's the name of that polyatomic ion? Perchlorate. Perchlorate. And what did we say about the rule was? Ate goes to ick. So this is perchlorate. It becomes
Hydro.
no hydro. Perchloric. Okay. A goes to ick. It's called perchlorate. So the acid is perchloric. There's no hydro here, right? Hydro goes with the binary. Yeah? Okay. Does that make sense? You see how we did that? No hydro with it? Because it's an oxyacid. You just say perchloric acid, that's it.
Okay.
8 goes to ick. But you do have to know the polyatomic ion before you can do that.
Okay. I see what you
Okay. Yeah?
Thank you.
Okay. So do you think we got them all right? Okay, so it helps to know which group we're talking about naming, right? It helps to know, are we a binary acid? Then we know we have to put hydro. If we're an oxyacid, don't do that. So first decide which group you're in, and then you can talk about naming that. So let's just double check. Sodium sulfate, perfect. Ionic. Calcium sulfide, that's ionic, great. Copper 1 chloride, ionic, awesome. We have to have a Roman numeral. Chromium 3 oxide, remember chromium's in the middle, so I always need to put a Roman numeral with that. This is an acid. It's an oxyacid. You have to know that that's chlorate. So that becomes chloric acid. Sodium oxide, that's ionic. Manganese 3 oxide, very good. Ammonium bicarbonate. Copper 2 nitrite, very good. This is molecular, so it's dinitrogen monoxide. And then tetraphosphorus dicoxide, that's molecular. This is molecular. Perchloric acid, very good. Dinitrogen difluoride, that's molecular. Sodium hydrogen sulfate, this is not an acid. This is what polyatomic ion, very good. This is molecular, very good. Tetraarsenic hexoxide, ferrous nitrate, very good. Nitrite, sorry. This is an acid, it's an oxyacid, so it's called bromic acid because it was bromate. This is our potassium potassium carbonate. That's carbonate. You got to know those polyatomics. Potassium carbonate, dihydrate. This is hypoiodous acid, and this is cobalt 2 sulfate heptahydrate. Does that make sense? Okay, so if you want to take a picture of that and study and practice that, you can. Okay. And then that finishes chapter 2. So our test on that is coming up like this weekend. Chapters 1 and 2. All right, so we'll start with chapter 3 on Thursday. Whew, good job, everyone. Okay, chapter 3 on Thursday. Oh, I'm sorry. Sorry. Okay, and if you want to get a picture of that, go ahead.